So should we start now?
Yeah, I'm ready. Yeah, it depends. I mean, if all are ready, fine, we can start. No problem.
Yes. Let me just introduce you, sir, once, then we'll start. Good morning, dear participants. Let me introduce you all to our next expert guest, Dr. Animesh Mandal. Dr. Animesh Mandal is currently working as an associate professor in the School of Minerals, Metallurgical and Materials Engineering at Indian Institute of Technology, Bhubaneswar since 2012. Sir was a postdoctoral fellow at Metal Processing Institute, Worcester Polytechnic Institute, Massachusetts, USA, where his work focused on aluminum alloy development for automotive industries. Sir has completed his Bachelor of Engineering in Metallurgical and Materials Engineering from IGIT Sarang, Odisha, and received his MTech as well as PhD in Metallurgical and Materials Engineering from the Indian Institute of Technology, Kharagpur. He has more than 50 publications to his credit and 3 patents presently. Currently, he is supervising 6 PhD students and has supervised 10 MTech students. His research interests includes solidification processing of aluminum alloys and its composites, including semi-solid processing of the same. Sir is today going to deliver his lecture on processing and properties of aluminum-based alloys and composites. Welcome, sir, and over to you.
Okay. So, good morning, everybody, and thank you, Dr. Mishra, for this introduction. So I would try to keep this in an interactive mode. So, if anybody has any doubts, any participants, so please feel free to stop me, or you may also note down the questions, and you can ask me at the later. So, whatever is convenient to you. So, I am also open to you can interrupt me, and you can clarify your doubts then and there. Okay, so that's also fine. Since this is an FBP, so I think that's also works well. So as Dr. Mishra already introduced, so and the topic you can see here. So here we'll be discussing about this processing and the properties of aluminum-based alloys and composites. So the topic looks, I mean, very broad. Okay. So now I try to zero in on some of the important and most relevant topics in today's context. Just to introduce you about our school, SMME, as we call it in short. So we started our MTech program in the year 2012. So that is how we started the school, and thereafter the PhD program was introduced and followed by the BTech and the dual degree program. So these are the respective current strengths. So it's almost running full strength, and we have currently 12 faculty members, with 8 being the regular ones, and we have adjunct as well as the visiting professors. And this is the upcoming new building, which is yet to be handed over to us. So hopefully we'll be getting it within next few months. So the outline of the today's presentation will be a very brief an idea to give an overview of the classification of your aluminum alloys. So what are the main applications of these aluminum alloys, and we'll also then move over to how these composites are made using these aluminum alloys, like your metal matrix composites. Okay, and we'll focus more on your aluminum matrix composites, as the title suggests, and we'll touch upon some of the advances in your aluminum alloys, what's going on in your aluminum alloy development program all around the world. So we'll be trying to touch upon that, and we'll end with some of the research or the scope of further research in your aluminum alloys. So as you must be aware that, so there is a great push for use of your aluminum alloys, especially with this Make in India, and a great push for your manufacturing sector. So aluminum alloys are finding more and more use, and also lots of investments are coming in this particular class of aluminum alloys. So after steel, probably it's the aluminum alloys where lots of funding is going to come in the next few decades. So that's what is the projection as far as your aluminum alloy goes. So to begin with, a very brief introduction to your aluminum alloys. So if you see aluminum lies somewhere here, and if you are aware of aluminum alloy literature, so a good number of alloying elements have been added to your aluminum to increase its properties, because as you know, aluminum is a very soft metal. Pure aluminum is very soft, right? It has a Vickers hardness of around only 20. Okay, so in order to increase the strength, the corrosion resistance, and many other properties, maybe nowadays people are talking about thermal conductivity or high thermal conductivity aluminum alloys. So different elements have been added to achieve the properties up to various levels. So silicon, phosphorus, you name it. So most of these elements have been added, so that interaction has been well studied, but there's lots of scope even more to study. With the advent of more and more advanced calibration techniques, so new informations are being revealed about your aluminum. So as far as your metals goes, so aluminum is considered as a new metal because it was discovered quite late, if you compare it with your copper, iron, or other metals. So aluminum is relatively a new metal in that sense. So if you see the major elements which are added to your aluminum alloys. So the major alloying elements which are added are copper, manganese, magnesium, silicon, zinc. Of course, lithium is not that common, but as far as their ASM classification, it's still remaining. But these are some of the very frequently added major alloying elements. So accordingly, you can have a range of aluminum alloys which can exhibit a wide range of properties. So when I tell properties, mostly we are referring to your mechanical properties, but it could also be other properties as well. So depending on whether I can cast my aluminum alloy or not, or whether that aluminum can be further deformed. So we have two broad ways of classifying these aluminum alloys. So one is, we call it as a cast aluminum alloy, and there is a certain ASM designation which is followed. Okay, for example, I will not read out one by one, so that's going to take a lot of time. So you can see these are some of the alloy designations. So for example, let us pick say 2. So when I tell 2 series, it means that the major alloying element is the copper. Okay, and you can have other alloying elements as well, but the major alloying element is the copper. So likewise it follows for, so for example, there are certain unused series as well till date, and if we have many other alloying any other alloying elements which do not fall in this particular category, so it can you can club them under your 9x series. So that is how you classify. It's nothing but a 3-letter designation followed by 1 decimal. Okay, so again, these decimals also have some meaning. So I think we will not have so much time to discuss. Okay, if you have any doubts, we can discuss later on. Then coming to the wrought aluminum alloys. So as I tell wrought aluminum alloy, it simply means that these are not the final product. In fact, they are the semi-finished product. That means it could be an ingot, it could be a billet. Okay, so which needs to be further processed using some, say, mostly a plastic deformation operation, like your rolling, extrusion, forging, or any other plastic deformation for that matter. And here, if you see carefully, so this is a 4-letter designation. That's the nomenclature which we follow for your wrought aluminum alloys. Again, suppose let us pick one, say 5 series. So when I tell 5 series of wrought aluminum alloy, what it means is that it is a magnesium containing alloy. That means magnesium is the principal alloying element. Of course, you may have other alloying elements as well, but magnesium is the primary alloying elements. That's how you need to understand. So cast and wrought. So all metals for that matter. So you can easily categorize into a cast category as well as a wrought category. Cast, it simply means that casting is the means by which you produce the end product, whereas in wrought aluminum, wrought metals, it means that you can further deform them to get the end product. So that's how you distinguish between a cast and a wrought aluminum alloy. So once highlighted in your blue, you can see, so there are again, you can further classify them on the basis of whether that particular series is heat treatable or not. For example, in the cast, the 2 series and the 7 series, okay, containing copper and zinc respectively. So that is class can be called as your heat treatable series. So what it means that if you heat treat it, you are going to, or you can expect an increase in the strength of these alloys via several mechanisms, and one of the primary mechanisms being the precipitates, formation of precipitates. So likewise, even in your wrought aluminum alloys, so you have the series, the 2 series, the 6 series and the 7 series. That means adding these alloying elements will form certain precipitates in your aluminum alloys, and that's why heating them will lead to an increase in the properties. Of course, there is a particular sequence you need to, or there is an order, or certain temperatures have to be followed, certain holding time have to be followed, so that you can get an optimum or the maximum benefit out of this particular addition of this element. So that has to be kept in mind. So all these studies are done under the broad category of something which we read in metallurgy. We call that as a heat treatment. Okay, so heat treatment of alloys. When you read, when we teach the students, we talk about all these different precipitation mechanisms which lead to hardness of this particular alloys or increase in the strength of these alloys. So one thing is very important for you to understand, that the solubility of these elements in aluminum impacts the properties of these aluminum alloys. Okay, so that's very, very important. So, um, so the solubility of which elements? So, for example, this table, if you can see, all the elements have different solid solubility. Only the maximum solid solubility is mentioned, and you can get all these values if you are aware of the phase diagram. Okay, from a binary phase diagram, for example, if you pick the aluminum cadmium phase diagram, so you can easily note down from that the eutectic temperature as well as what is the maximum solubility. It is represented in 2 ways, one as weight percentage and other as atomic percent. So whatever is convenient to you, you can use it. So the solubility has a lots of implication on bearing on the properties of your aluminum alloy. So that's very, very important. The other important thing which is to be noted when we deal with aluminum is the hydrogen. Okay, so hydrogen is quite, is, I will say, undesirable in your aluminum alloy. So we need to keep the hydrogen to a minimum. Okay, you don't, and hydrogen, if you see the diagram, even in solid aluminum, okay, so this is the pure aluminum melting point. So the melting point of pure aluminum is roughly 660 degrees centigrade. So that means towards the left, what we are seeing is, even in the solid state, hydrogen is diffusing into aluminum. Okay, and as it melts, you can see there is a sudden pickup or immediate pickup of hydrogen, and in the liquid there is an exponential rise in solubility of hydrogen. So that is what this particular plot tells you. It tells you about the hydrogen solubility in pure aluminum as a function of temperature. That means, and if you do not remove this hydrogen before you cast this liquid aluminum metal into your molds, you're going to end up in different kinds of defects, which are related to the porosity, blowholes, wormholes, so many kinds of defects. And so that's why hydrogen is quite undesirable in your aluminum alloy. So that means you need to find a way by which you should be able to drive out this hydrogen from your molten aluminum. That's very, very important. So that's one of the very, very key things when we talk about your aluminum alloy, when we talk about melting and casting of aluminum alloy. So that has to be kept in mind. So now just I have kept one slide only on the different heat treatment designations. I think we'll skip this because anyways we're not going to details of all this. Again, for there are different kinds of heat treatment which is possible or which can be given to an aluminum alloy. So you can see here the nomenclature all the way starting from T1 to T10, and each of these designations have a meaning. That means if you treat the alloy using T1 or if you treat the alloy using this T10 condition, so you are going to get or generate a different kind of microstructure, and consequently you are going to generate a different kind of properties. Okay, so that's the reason why you have different kinds of treatment. Again, it depends on the, of course this is uh, applicable only for your heat treatable alloys, be it a cast alloy or be it a wrought aluminum alloy. So this is the designation. So I am not going to read out all of these. So there is a scope, that means given an alloy, okay, given a heat treatable alloy, so you can play with the microstructure of this alloy by following all these different kinds of processing techniques, so thereby you can generate different, that means the same alloy, the same composition, you can have different kinds of properties if you follow these particular steps. Okay, so that's something which you need to understand. So that the similar thing is even done for your steel, since in your undergraduate you also read about your steels, right? Like heat treatment can lead to different I mean, if you give different types of heat treatment, or you can generate different types of microstructure and steel. So the same follows even for your different class of your aluminum alloys as well. Okay, so the kind of element that's present in this aluminum alloy will dictate different kinds of different sequence of precipitation in your aluminum alloys. So that's why different alloying elements will have a different bearing on your properties, because it's going to generate different kinds of precipitation. This microstructure only shows that you can see this length scale is 50 nanometer, and these are the kinds of or size range of precipitates which you are seeing. Not only that, you are seeing the different morphologies, like the this like the dotted ones, the small ones, you can have this elongated precipitates. So different morphology of precipitates also can be generated. So that's very, very important. So all this heat treatment, different heat treatment will generate different size and volume fraction of your precipitates, which is going to affect your properties. So as we are discussing about your melt practice, so when we talk about your aluminum alloys, or when you want to prepare, be it a cast aluminum alloy or be it a wrought aluminum alloy, you need to follow a certain steps. That means a series of steps need to be followed so that you can get a sound casting, meaning a defect free casting. Okay, and for that to do, you need there are many steps. For example, you need to choose the correct composition. Okay, you need to choose the correct crucibles where you melt. You need to choose the right stirrer and the stirring mechanism, okay, whereby you can remove all your hydrogen from your molten aluminum alloy. And finally you need to, so this step is nothing but you are essentially trying to remove all the hydrogen from your molten aluminum before you do the final casting into your mold. So there are series of steps which you need to follow so that you can get a really good microstructure, and most importantly a defect free casting. That's very, very important. So if you have any doubts, you can ask me later on maybe, so I can explain it to you. So now going to a little bit of basics. So I remember in the last time when I presented in one of the FDPs, I explained it in detail. So I'll quickly go through this. For example, here what you see is this microstructure of a pure aluminum casting. So this what you're seeing is the transverse cross section, okay, and this you're seeing for the same casting, you can see this is the longitudinal cross section. So this what essentially you're seeing here is nothing but your grains and the grain boundaries. And since it's very coarse, so you're able to see or these can be seen even with the naked eyes. So these are therefore these are called as their macro structures. So we can call it some we can also call this as so some textbooks also call this as microstructure, but essentially since you are able to see this using your naked eyes, so you should be calling this as a macrostructure. Now let's see what's happening here. Okay, for example, this is the casting, right? So and that means this is the mold wall or the die wall, whatever you can call it. So what's happening here is that so whenever the solidification starts from this mold wall, you can see what we get is essentially the formation of your dendrites. So these are called as the primary dendrites, and you have branching from the primary dendrites. So those are called as your secondary dendrites. So the manner in which this particular phenomena can be, the growth of the dendrites can be controlled is dictated by several factors. Okay, there are many factors which can control whether I will have a long elongated grain or if I can manage to have an equiaxed grain. So that's possible to do using different techniques or different processes need to be followed. For example, here all these any solidification process, it can be divided into two broad phenomena. That means one stage is the, we call this as the nucleation stage, where some nucleation has to occur, okay, and then the atoms get attached one by one in a periodic arrangement, and thereby what you generate is nothing but your grains and the grain boundaries. So that's how the concept of your dendrites, grains, and grain boundaries. So why this is of such a significance? Because all of these, okay, have very important role to play when you talk about the properties of your materials, be it I mean any property for that matter. So though here we are mostly focusing on the mechanical properties, so it could be any properties for that matter, and you need to precisely estimate this grain size or the grain diameter, what you call. Also you need to quantify this secondary dendritic arm spacing. That means spacing between this secondary dendrites. So there are many techniques. So one of the most popular technique by which you can do is your linear intercept method. That means you need to take lots of frames of the microstructure, and nowadays you have softwares which will give you these values, because you need to quantify this microstructure so that you can relate them with the properties which you get. Okay, so that's very important. So this is the basic about your dendrites and the origin of dendrite, the grains, and the grain boundaries. For example, so that means refining these grains is very important. So if you are aware of, there is a term called as the, or equation called as the Hall-Page equation, so which talks about how the yield strength of a material is related to the grain size. So as you have smaller grains, so you expect to have higher yield strength in a material. So that means the basic, so the very idea of any metallurgist or a material scientist is always to reduce the grain size of a material. For example, this type of grains, we call this as a coarse columnar grains, okay? And if you add, so how does it happen? So how does this transformation occur in the first place? It's not going to happen on its own. Okay, that means you need to add something to this particular molten alloy. That means to this molten aluminum alloy, and thereafter, after the solidification, you can expect this type of grains. So what is to be added? Certain particles. Okay, certain particles like your Al3Ti in aluminum. Okay, Al3Ti particles. Then there are certain particles like your titanium diboride. They are very commonly added so that these particles will act as substrates for nucleation of your alpha aluminum grains, and thereby you will be generating a fine grained material which is expected. Okay, now there are so many kinds of grain refiners which are added. Traditionally, you have this aluminum titanium boron alloys which are added. You have aluminum titanium alloys which are added. Aluminum boron alloys are added. So all these binary and ternary alloys are added. So the So what does this alloy contain? This alloy essentially contains these particles, and these particles, when added to the molten aluminum, is going to act as substrates for your nucleation of your alpha element, and thereby you will be generating a fine grain material. So that's the basic understanding, and this mechanism is called as your heterogeneous nucleation. Okay, and also traditionally these are the types of grain refiners which have been used. So aluminum titanium boron based or aluminum titanium carbon based, but all of these have certain merits and demerits which will be and that's why there is a need for new grain refiners. So many foundries are still working to develop newer and newer grain refiners so that you can get a very, very fine grain material. So this is something which is desirable. Okay, you don't want this kind of microstructure. So why do we need fine grains? Though we spoke about that it's the strength, but it's not only the high yield strength that is improved by having a fine equivalent strength. So if you have fine grains, your toughness improves. There is something called as hot tearing. That means you will not see any cracks on the surface of the castings. So hot tearing is a very as your casting score. Okay, then if you have fine grains, you also have a uniform distribution of the other phases, uniform distribution of the microporosity. Then you can improve the extrudability of that particular alloy, and machinability increases many folds, and as a result your good surface finish. So the generating a very, very fine grain material is very, very crucial to achieving a good casting. That means all the foundries, so the very objective should be to refine the grains as much as possible. So some of the casting techniques which are used for your wrought aluminum alloys are so there are many casting techniques, but these are the two very important techniques which are used worldwide. So one is your direct chill casting. Okay, that means here you produce huge ingots or the billets. So what the process is something like this. So initially this dummy block which you call it, so it's placed here. Okay, so it is placed here. So you can see the arrow pointing towards the lower direction, meaning it is descending hydraulic ram. That means as the liquid metal comes, and after a skin of this solid metal forms, slowly this particular hydraulic or this dummy block starts to descend downwards. So as a result, what you're creating is a huge ingot. So here that means you need to create a kind of underground well kind of thing. So where you have the provision of movement of this particular hydraulic ram, and thereby you get this castings. And if anybody has visited Nalco Anugul, so you should be seeing this particular DC casting setup. They produce different kinds of aluminum alloy. So this is one way of producing wrought aluminum alloy. So the other way of producing wrought aluminum alloy is your propersy casting. Okay, so what is done here is, for example, here you have this water cooled wheel. Okay, you have this hot liquid metal being poured here. Okay, and it gets solidified, and finally it's brought out in this particular manner. And this particular technique as far as is mostly used in your European countries and also in the US. So Italy uses this particular process quite extensively. So it's called as propersy technique. So these are the two techniques which are majorly used for producing this wrought aluminum alloys, because which has to be further deformed. Okay, so yes, just to share you the pictures, you can see. So this is how your DC cast ingots. So these are the actual DC cast ingots which you are seeing here, and these are the propersy ingots. Okay, you can see it's almost rectangular in cross section and long elongated. So these are further, you can deform this to get whether it may go to a forging plant, it may go to a rolling plant, or any other plant. So this is how, so the process looks quite simple, but there are lots of challenges to make this. Almost you can see it's a defect free sample. Okay, so to make this, of course, it requires lots of lots of science and technology has gone into, so to make a defect free sample. So, but as far as your cast aluminum alloy, there are lots of processes which are available to produce your cast aluminum alloys. So, some of the most important or the most prevalent techniques for producing these cast aluminum alloys is nothing but these are the three techniques. So one is your high pressure die casting, that is called in short, it is called as HPDC. So where in you have this liquid metal poured into a short sleeve, we call it, and it is rammed into this at a very, very high pressure, and it gets and fills the die. Okay, so this is one of the very popular technique for producing components whenever you need on a large scale. It's a large scale process. That means you do not produce few hundreds of components using this. Generally, you want to produce millions and millions of components using this. So only the limitation of this particular process is that you cannot cast a huge casting using this particular process. So till now, at least to my knowledge, castings up to 2 kilograms have been cast using high pressure die casting. So the most common ones are typically around 1 kg, but and it can go to as low as few grams. So that's the beauty of this process. So you can go to a that means very, very small components with a very high precision can be produced using your high pressure die casting. And this is a very common technique which we use in our labs, that is called as your gravity die casting. We just pour it into your molds which you have created, and it gets solidified within this permanent molds, right? So this is the gravity die casting which we use very commonly in our labs. And the other technique which is used is your low pressure die casting. As you can see, it's a counter gravity process where your liquid metal is sucked into this particular dies. So it's a counter gravity process. So this is a gravity process, and this is by pressure, and this is a counter gravity process. That means you can draw the liquid metal to fill this particular die, and you can control the velocity, and the die filling is very, very uniform, hardly any turbulence, and as a result, the components which you get using this particular process it's almost a defect-free casting. That means the castings which you get are almost defect-free due to the very nature of the process. So these are the very popular techniques of producing your cast aluminum alloys. There are many techniques. If you must have gone through the undergraduate textbooks, you have many techniques which are available, but these are very common in your industry. So industries use these processes quite profusely. And among these cast aluminum alloys, the systems which are very popular are your aluminum silicon alloys. Okay, so hardly we use for practical purposes, we hardly use any binary alloy. So it's a multi-component alloy, and the most important alloying elements which are added to your aluminum silicon alloys are your magnesium, copper, and or a combination of copper and magnesium. That's very commonly used. So the reason being, you can see if you add magnesium and copper or both, so you impart some amount of, that means you make that alloy as precipitation hardenable alloy. That means when aluminum silicon alloy by itself is not a precipitation hardenable alloy, but the moment you add magnesium, so what it will generate is some particles called as Mg2Si. Okay, and those particles are, you can create precipitates of Mg2Si. So that's possible. Similarly, if you add copper, as we know, you can create precipitates of Al2Cu. Okay, and likewise, if you add both, you can have different kinds of precipitates when you add both of these. So that means what essentially you're doing is, by adding this alloying elements, you're making a non-precipitate or non-heat treatable alloy into a heat treatable alloy. And why is it so? Because you can increase the strength of these alloys by proper heat treatment. Okay, for example, the alloy wheels which you see in most of the cars nowadays, okay, are all made using aluminum alloys. So hardly we use any steel alloys, steels for making this alloy wheels. It's mostly different grades of aluminum alloys. Of course, it's an aluminum silicon base, but these compositions could vary here and there depending on the company. I mean, which company prefers which kind of composition, of course, keeping in mind the strength into factor. So apart from this, to all these alloying elements, these are some of the elements which are added, but in very, very trace amounts. Okay, so these are called as inoculants. So it could be strontium, it could be phosphorus, it could be titanium, boron, iron, and manganese. So these are added to these particular alloys to impart certain properties. Okay, mostly strength, but there are other properties as well, in some cases to improve the ductility as well. Okay, so these are the elements which are frequently added in different ratios so that you can improve these properties. So if you remember, or if you are aware of a binary phase diagram, so the aluminum silicon alloy, if you look at the phase diagram, though I'm not showing here. So if you are aware of the basics of your phase diagram, so you have a eutectic composition, okay, like, and all the alloys which are towards the right, we call that as your towards the left are called as your hypoeutectic alloys, and the alloys which are towards the right of the eutectic, they are called as your hypereutectic alloys. So accordingly, your microstructures can vary. So you can see this silicon, the silicon which you have here in eutectic as well as your hypoeutectic. So these are all needle in shape. You can see almost needle in shape. So hypereutectic, you can see in addition to the needle shape silicon, you also have this primary silicon, which is quite coarse, and both of these morphologies, that means this needle shape as well as this polygonal primary silicon, generally you do not desire in this kind of alloys. So that's why the reason is, as a result, what you do, so how to modify this morphology? So you can modify the morphology of this needle shaped silicon as well as this polygonal silicon using the elements of like strontium and phosphorus in different amounts. Okay, so this is something which you need to understand. So this a very, very trace amount, that means maybe in the of the order of few ppms, that is good enough to change the morphology of this particular alloys. So this is in very brief about your aluminum alloys, wrought aluminum alloys and your cast aluminum alloys. So whenever you hear to or listen about your cast aluminum alloys, the first alloy system that should come to your mind is your aluminum silicon alloy. So that's we call that it's the bread and butter of your casting industry. Okay, so because most of these processes which demands very good fluidity, okay, or very good castability, so you have, and you have to have silicon in it, because silicon or addition of silicon improves the fluidity of this particular alloy for various reasons. Now coming to your metal matrix composites. So as you must be aware of, all the metallurgists as well as the mechanical engineers, you deal with a good amount of composites. So like a lot of people work on polymer matrix composites, and good amount of, and also people work on ceramic matrix composite. But here what we are going to discuss in very brief is the metal matrix composites. In short, we call that as your MMCs, right? So if you see the scenario of your MMCs, of course, it's if you see this is a Scopus document, so which I try to grab, you can see, of course, there is a great interest in your MMCs. So over though this the data is till 2015, it's on this steady rise. Okay, so there is a great demand for your MMCs, and this shows the number of publications, okay, year wise. So initially, of course, the work on MMCs picked up maybe in the late 80s, I would call. Okay, and there you can see there is a surge in use of this MMCs, not only the publication wise, even the use wise, there has been an increase, but of course for a certain niche applications only. So it's you cannot use the MMCs for any common applications, because cost again is the limitation. Okay, but nevertheless, for any niche or advanced applications, MMCs has been used and will be and will continue to be used. Okay. Now, if you see a country-wise distribution where the amount of work on MMCs are going on, you can see United States is leading, followed by China, and India is not far behind. You can see there's good amount of work even going on in the Asian countries, okay, like China, India, Japan. A good amount of work is being, or a lot of focus or emphasis is being done or is given to your metal matrix composites as well. So, and the major consumers for this metal matrix composites are the automotive sector and the aerospace sector in special. Okay, so they are the major consumers of these particular materials. Even uh, um, uh, uh, the sports industry uses this particular metal matrix composites, especially though I'll be talking about aluminum matrix composites. The titanium matrix composites are being heavily used in your sports industries as well. So as you must be aware of, this is a very common are the important components of a composite material. So as you know, the matrix, which is the bulk phase or the major phase, and you can have this reinforcement, though I have drawn this reinforcement as if it's a particulate, so it could be in either form. It could be a fiber, it could be a whisker. Okay, the only requirement is that it has to be a ceramic or a metal or an alloy with a very, very high melting point. So it could also be an intermetallic. Okay, so that the reinforcement could be anything, and its morphology, as I already told, it could be any of these, the particulate, fibers, or the viscous as well. And the third important thing which should be given lots of emphasis, so at least the materials engineers deal with this in quite detail, the interface, which is very often ignored. Okay, but it should not be ignored. So interface plays a very, very crucial role. So what is the interface? The interface between the reinforcement and the matrix. So interface, if you examine, so as far as possible, it should be as clean as possible. That means if you look into this interface using a scanning electron microscope, so you should be able to see that you do not form any interfacial products in this interface region, because if the interfacial product is weak, it can deteriorate the overall mechanical properties, or in for that matter any properties of your composite. So the interface plays a very, very important role apart from your matrix and the reinforcement. That means, so what we can summarize is that these properties of this composites is a strong function of not only the major phase, okay, and the minor phase, that is the reinforcement, but also plays a very, very important, or the interface plays a very, very important role in dictating the properties. Because if you see the strengthening mechanisms, if you are aware of the several strengthening mechanisms which we cover in a typical metallurgy course, load transfer mechanism, the dispersion strengthening mechanism, and your dislocation strengthening due to your coefficient of thermal expansion mismatch, or strengthening due to grain refinement, all of these factors, and there are a few more, but these are some of the important strengthening mechanisms. So they can be influenced by this interface. Because the interface is weak, so all of these could be affected severely. So that's the reason interface has to be, or characterizing the interface in a metal matrix composite is very, very important. So like in a typical composite material, like to show you one example, so this is an aluminum titanium diboride composite, so which people are working on. So I have also worked a great deal on this particular composite. So you can see this composite, if you can, this is the interface between your aluminum and your TiB2. So what here we are trying to see, or this is from a paper which is by one of the authors. You can see that the interface we are trying to see here, and you can see the interface is pretty much clean. That means you do not have any such products which are formed between your aluminum and the reinforcement. So that is one of the very important things or aspect of your interface. Because why focus should be laid on your on the interface is that because it occupies a large area in your composites. Okay, and the interface, again, just to reiterate the point, it becomes more important, especially when you're dealing with metal matrix composite and ceramic matrix composites, because the processing temperatures are quite high, right? And at those high processing temperatures, so there are chances that you may end up having some reaction products at the interface. Okay, so that's why it becomes so, it may not be that significant when you're dealing with any room temperature processing, okay, or a very, very low temperature processing. But in metals, all the processing are generally done at relatively high temperature. So that's why the interface or characterizing the interface becomes very, very important. So, and the other factors are, in crystallographic terms, the ceramic metal interfaces in composite generally are incoherent. That means ceramic meaning, let us treat this as a ceramic, okay, and let us call this as a metal, right? Sometimes this, in most of the cases, they are incoherent. Incoherent meaning you will not have one-to-one matching between these planes of your particle and the matrix. So that's a very common thing, okay. And these interfaces are efficient sinks or vacancy sinks which can provide rapid diffusion path. So that's why you can see that more the number of, or more the volume fraction of your interface in your material, okay, so you are, that means affecting, or you're changing all of these parameters, the diffusion or the diffusion speed or the rate at which your solute elements can diffuse from one end to the other. Then this interfaces can also act as sites for segregation of different solutes, okay. So that's why. And also, when we talk about wrought aluminum alloys or heat treatable aluminum alloys, okay, so you'll have precipitates, right? So the interface also alters the precipitation sequence in these alloys. So that's why the importance of you need to understand the importance of interface in your metal matrix composites, because it can influence the properties quite significantly. It's not only about the matrix and the reinforcement, but also the uh, interface. Okay, so that means whenever you choose any particular processing step, you need to be very sure that you do not form any interfacial products whatsoever. Okay, so that's very, very important. So coming to your aluminum matrix composites, so as we have already discussed, so these, you can use any matrix for that matter. So whether you want to produce a cast metal matrix composites, or whether you want to produce a wrought aluminum metal matrix composite, so you can choose the matrix as per your need, or as per the application. And some of the very common reinforcements, or the properties of this common reinforcements, are shown in this particular table. You can see. So these are quite common, like titanium diboride, titanium carbide, alumina, zirconium diboride, Mg2Si, aluminum nitride, and the most common being your silicon carbide. Okay, the aluminum, so silicon carbide system has been very, very well studied as far as your aluminum matrix composite goes. So you can just Google it, and you can see I think few thousands of pages just corresponding to your aluminum silicon carbide composite. Even some of these companies, like the automotive companies, still use this particular reinforcement for many, many applications. Now, if you have a look at these properties, you can see they're relatively denser than aluminum. So aluminum density being 2.7, okay, only the magnesium is lighter, but more or less others are quite denser, okay. So, and all of them have relatively high melting point, and the Vickers hardness is quite high. Of course, they are ceramic. You can see the Vickers hardness is pretty much high. The elastic modulus of all these are pretty much high, except for, say, Mg2Si. The thermal conductivity is on a lower side. You can see, except for your TiB2 and your silicon carbide, you can see all of these have a little bit relatively lower thermal conductivity. So that's another area where people are working on, or searching or looking for a particle which has relatively higher thermal conductivity, so that you can make a composite which, so that you do not sacrifice the thermal conductivity of that particular alloy. So there is a need, or a need for development of, or to generate or look for some particles which have relatively higher thermal conductivity. Okay. And of course, as I told, so nowadays people are, since one of the main attributes of your of making your metal matrix composites is the having higher elastic modulus, because you're introducing a phase with higher elastic modulus. So the overall elastic modulus is going to increase significantly. Like we are just to summarize this, your Ashby plots, if you see, if you are aware of this Ashby plots, so Ashby plot is nothing but it gives, you can pick any two properties, okay, and it will generate this kind of plots. So what it gives you an overall idea of, for selection of materials. For example, you know that metals have a little bit higher density, strength, and the modulus is quite high. Similarly, for ceramics, it's quite high, also it's quite high. Similar, and composites are somewhere in between. Okay, so that means this particular graph give you an idea of, so what are the different properties of your material in at a glance. Okay, for just to make it a little more neat, you can see this particular diagram. It's the same diagram, but other content has been removed. You can see metals lie here, the ceramics, which are nothing but the reinforcements, lie here, and as a result, the composites are somewhere intermediate. So that means you are getting a balance between the properties of your metals and ceramics. Okay, so that means Ashby plots can be very useful for zeroing on the material properties, or it's generally used for your selection of materials. How do we process this aluminum matrix composites? There are n number of processes which are available by which you can process this aluminum matrix composites. So solid state processing is quite common, so which we are not discussing in this particular talk. As you're aware, these are some of the very common solid state processing: the powder metallurgy, the friction stress processing, the microwave sintering, spark plasma sintering. These are very, very common. So as far as liquid processing goes, so since we are talking about castings, right? So infiltration is one of the common techniques. That means where you can infiltrate the liquid metal through a preform of your reinforcement. That means you need to make this preform of your reinforcement, and you can pass, or you can infiltrate the liquid metal through that preform. So that's one way of making composite, and this is used generally when you want to have a higher volume fraction of reinforcement in the composite. Okay, but otherwise, casting is one of the most popular technique by which you can make your composite. Again, there are so many casting techniques. So stir casting, squeeze casting, centrifugal casting. So there are many more techniques by which you can make this composite. But there are certain, again, limitations of the casting, because you may not be able to introduce a huge amount of, or high volume fraction of reinforcement in a typical casting process because of the fluidity issues. Okay, so in that case, you have no other choice but to go for your infiltration techniques. There are other processing techniques which are available, but these are some of the very popular techniques which are used for processing of your aluminum matrix composites. For example, there are you can further categorize your aluminum matrix composites as far as the processing goes into two categories. So one we can call that as your conventional aluminum matrix composite. For example, if you take a reinforcement and you add to the molten aluminum alloy of your choice. Okay, so that's how you produce your conventional composite. That means you already have the ready-made reinforcement, and you need to find a means of introducing that into your liquid aluminum and finally solidify it. So this particular slide shows you the different types of your aluminum silicon carbide composite that is possible. Okay, so first one, here you can see you have this fine silicon carbide particulates. In the second case, you can see the silicon carbide particulates or particles, whatever you can call. So these are relatively coarse. Whereas in the third, you can see it's a mixture. That means you can have it's a combination of coarse as well as fine silicon. And you can see all of these microstructures are different. So as a result, you can generate different kinds of properties in all of these composites. In the same silicon carbide, just by changing the size, and not only that, by changing the volume fraction, you can play with the properties. Then the fourth case, if you see, so this is a silicon carbide fiber, okay, made using certain technique, by most probably an infiltration technique. So you can see this is also a composite where your fibers of silicon carbide have been introduced. Okay, and of course this property of this particular composite is going to be entirely different from all of these. And also you can see the properties. So the difference between this composite and the remaining three composite is in its the nature of the properties. For example, in this particular composite, you will have higher properties along the direction of the alignment of these fibers. Okay, whereas in the remaining three composites, the properties are going to be more or less isotropic. Okay, whereas in this particular case, the properties are going to be highly anisotropic because of the alignment of these fibers of your silicon carbide. So you can say all of these four composites which are shown here are aluminum silicon carbides, but all of them have different microstructures and you can generate different kinds of properties. That means just this name, so that means there is a way of naming this particular composites. Okay, that means because this name is sometimes it can misguide you. So you need to clearly specify whether it's in a particulate form, whether the silicon carbide is in the fiber form, or whether it's in the viscous form. So whenever you notify or this particular composites, you need to clearly specify the type of or the nature of the reinforcement. That's the or the morphology of this reinforcement. That is very, very important. And of course, the volume fraction has to precede this particular reinforcement. So that's that is a typical that is the way of addressing this particular naming these composites. So the other class of composites, we can call that as the in situ composites. So in this case, what happens? You do not add the particles from outside directly. So rather, what you do is you add certain raw materials, okay, which will react within the melt. As a result, it will form those reinforcements. For example, let us take the case of your aluminum titanium diboride composite. Okay, so here what's happening is, you can see these are the two salts, fluoride salts of potassium. Okay, one is the titanium salt, one is the boron salt. So that means if you mix this in particular ratio and add it to molten aluminum, so they can react and form this titanium diboride particle. Okay, you can see this beautiful hexagonal particles of your titanium diboride. So the only issue with this in situ composites is that yes, the particle sizes are really fine. Okay, but the problem is the issue is with this such kind of in situ composites has been the agglomeration. Okay, that means these particles tend to agglomerate with one another, and as a result, people have devised certain techniques by which you can at least minimize the agglomeration. So for example, if you do certain plastic deformation like your equi-channel angular pressing, okay, so you can de-agglomerate, or you can at least break those agglomerates and disperse within your matrix, and as a result, you can expect to have better mechanical properties. Similarly, if you have these different amounts of these particles in your say aluminum 4 copper alloy, for example, so this is the aluminum 4 copper alloy, and these are the composites, 4 different composites with different amounts of weight fraction of your titanium diboride. Okay, so here what is the plot shows you that. Let us first have a look at say aluminum 4 copper alloy. So what does it mean? So the round dots you can see. So this is the plot. So that means as you're aging, so if you are aware of your heat treatment, so if you age, that means heat it at certain temperature, you can see you attain a maximum hardness and then followed by a drop. Okay, whereas if you add these particles, okay, so that means here the time taken for peak aging, okay, is around, we call this as your maximum hardness is called as your peak hardness. You can see it's almost close to 40 hours, right? But when you add this particle like titanium diboride, so what's happening is hardness, of course, is expected to increase, but not only that, the time taken for it to reach this peak hardness comes very close to around 10 hours or 8 hours. That means from 40 hours in an alloy, by adding reinforcement, you have brought down the peak hardness of your composite. So that means what it's doing is is enhancing, we call that as your aging kinetics of this. That means having a composite is beneficial also for accelerating the aging kinetics, meaning your precipitation of this Al2Cu, which is present in this alloy, can occur at a much lower time, and that's a significant improvement. For example, you can see here from 40 hours you have reduced all the way till your 8 hours. So that's that has a very industrial implication as well, because you're going to reduce the heat treatment time. So the other application of your composite is that you need to make composite when you want to make a metal foam. So if you are if anybody is aware of metal foam, so like the foam you produce in your polymers, even the metals can be foam. Then you can make a foam out of your metals. Okay, and for that to happen, you need to make a composite. Okay, though here I'm showing the example of titanium diboride, you can choose any reinforcement for that matter, but again that has to be optimized depending on the size and the volume fraction. You can see here 6 volume fraction TiB2, it's able to give a very nice stable foam, we call it. Whereas if you have a lower amount of this reinforcement, you can see there is something, a dark color shaded area at the bottom of this foam. So here what we call this as your drainage of your liquid. That means this foam is not a stable form, and as a result your drainage of liquid is taking place, and this has something to do with the amount of titanium diboride which is present. So that means you need a higher amount or an optimized amount of this particular reinforcement so that you can create a stable foam. So that's another application of your a foam. For example, if you see this particular plot, this particle volume fraction versus particle size. So the preferred range is somewhere here. That means you cannot have very high particle size, neither you can have a very low particle size. Always you need to follow a certain range. Again, this range will depend on what kind of particle we are talking about, okay, which is the, what is the type of reinforcement we are talking about. Not only that, even the particle volume fraction also has a role to play. So that means particle volume fraction along with particle size will have a bearing on the stability of foam, else you will end up having this drainage of this liquid metal and you will not be able to get a stable foam for different applications. So this is how, and again I'm not discussing how this foam was produced. Typically it is produced using your titanium dihydride, which is a gas releasing agent, so that is used for producing this kind of foams. Now to summarize some of the advances or what's new in what's going on in your aluminum sector. So for example, as we spoke about your grain refiner, so there aluminum, titanium, boron master alloy was very commonly used. So nowadays what people are looking for is your aluminum, niobium, boron master alloys, okay, or grain refiners you can call it. So these have certain advantages over the aluminum or traditional aluminum, titanium, boron master alloys. For example, it has been tried out in certain hypereutectic aluminum silicon alloy, and you could see that you can not only grain refine this alpha aluminum, but also this primary silicon we were able to grain refine using this particular master alloy. Not only that, even if you take a pure aluminum, so you can grain refine this pure aluminum, or this refinement of primary aluminum is also possible using this. That means simultaneously also you can grain refine this primary aluminum as well as your primary silicon. So there are certain advantages of this particular aluminum niobium boron master alloy over your aluminum or aluminum titanium boron master alloys. The other thing is nowadays also people are working a lot on your different or development of your hypereutectic aluminum silicon alloys. Okay, so that's another important area where people are working on, because not only for improving the mechanical strength but also to improve the wear resistance of certain components. Okay, so aluminum silicon alloys, especially the primary silicon, plays a very important role in improving the wear resistance of this particular alloys. So I'm not getting the details of this. So one such aspect, one such study was done using different amounts of your magnesium. That means here what this particular study shows that if you continue or keep on adding magnesium to your hypereutectic aluminum silicon alloy. So remember, the hypereutectic aluminum silicon alloy contains primary silicon. Okay, and sometimes if you consider the mechanical properties, it's not desirable from a mechanical property point of view. So the study was carried out whether if we can add or go or keep on increasing the amount of magnesium in this particular alloy, so what's going to happen to this primary silicon. Indeed, you could see that if you keep on adding magnesium to this hypereutectic aluminum silicon alloy, so there is a complete suppression of this primary silicon. Okay, and that was something which we were aiming at. Okay, because in that case you can have the alloy with a reasonable strength and also very good ductility. Okay, and so the reason is because you are suppressing the primary silicon. And if you further heat treat this alloy, you can see the phases which you get. Okay, the Mg2Si phases which you can get and the silicon which you get are almost globular. It's almost spheroidized. That means it's almost round in shape, and this contributes to in the improvement in the ductility of your alloy. So another area where we are working on is whether adding addition of low quantity of certain oxides, whether it could improve the or it could decrease the size of your primary silicon. And indeed it's the word, because Al2O3 is a relatively a cheap reinforcement of the particle, so it is quite effective in refining this primary silicon in your hypereutectic aluminum silicon alloy. Similarly, the same alloy, we tried to cast it using a technique called as a suction casting, where it's a very high cooling rate process. So it's also possible to generate almost, I will say, a nano-sized eutectic silicon, because if you see, of course, not the entire volume fraction, but there are points. There are you can see from this particular microstructure. So this is a 500 nanometer bar, right? So this is quite less than your 100 nanometers. So it's possible to generate nano eutectic, that means nano site eutectic silicon using a fast cooling rate process, and the properties which we have achieved for this is quite exceptional high. It's very high for a normal hypereutectic aluminum silicon alloy. And as far as the processing goes, so last time, even in the last FDP, I discussed about this process. So this is a relatively new process as far as your aluminum alloy goes. It's a modified version of a sand casting process. You can see it's called as a ablation casting. So where you can ablate or erode away this particular sand mold using a jet or a spray of water. Okay, that's possible, and the reason is this technique has lots of merits because you can achieve a very very high cooling rate in this particular casting, which otherwise you do not achieve in a typical sand casting process. And as a result, what you get is a very very fine microstructure, which I'll be showing it to you in the next slide. So here the trick is, or the I'll say the secret is using or designing an inorganic binder which is soluble in water, so that you can as your solidification proceeds and as you start this jet of water, so immediately your particular sand gets ablated, okay, due to this jet of water, which is generally kept at 65 degrees centigrade. As a result, you achieve an extremely high cooling rate in this particular modified version of the sand casting. You can see the microstructure is very very fine. You are hardly able to see this eutectic silicon, which is very very fine. So you can see the cooling rates experienced is very close to the one achieved using a metal mold. So that's the beauty of this process, and as a result you are able to generate such microstructures, and as a result some even the Hero Honda is already using this particular process to produce certain components, some auto components. So another interesting process is that it's a very low cost process. For example, here what you can do is, this is called as your low shear slope casting. So what you can do is, you can pour the liquid metal here. It all the way traverses all across this, all along this particular slope. Okay, and there's a you can also vibrate this particular setup. Okay, there is a, you can, so it's possible. So you can see, just using this setup you can easily grain refine or achieve a fine grained material very very easily. So it's a very very effective way of introducing vibrations and thereby breaking away the, or breaking down the grains in your solidifying aluminum alloy. So this is a slope casting process, and I think lots of labs are using, and some of the industries, and this process has also gone into some of the industries to produce we call that as your non-dendritic structures. So another important area, so as a mechanical engineer or a manufacturing engineer, so you must be interested on, and lots of work is going on in your additive manufacturing of your aluminum alloy. Though here I have not specified the numbers, it's all written in terms of X, but the target is that this it's a huge market. Okay, so all it has been applied to almost all the materials which you have around you in such a short span of time. Okay, and aluminum alloy is no such exception, and the market is that is the projection till 2028. Okay, so it's expected that the market is only going to pick up. So I'm not getting the details of this additive manufacturing. As you must be aware, it's nothing but your layer by layer processing of certain components, right? So that's the beauty. You can technically make any complex shapes using this particular process. Like one such component, for example, you can see this particular frame of this motorbike is entirely made using an additive manufacturing technique, because if it were made of some other process, maybe it would be quite, it would have lots of joints and rivets, right? So but since it is made of your additive manufacturing technique, you don't have such joints whatsoever. Okay, so, and it's a very promising technique, but of course it has its own limitations as well. So one being the cost. Okay, one major limitation being the cost, but from a microstructure point of view also there are certain limitations as of now, but I am sure it will be overcome within in the due course of time. So lots of groups are already working on this additive manufacturing of your alloys. So what's the scope of this research in your aluminum alloys? So lots of scope, though I have listed only few of them. So the few of them being, production of your cast aluminum nanocomposites. See, aluminum nanocomposites using powder metallurgy has been investigated and studied in quite details, and it's relatively easy to manufacture. But again, the using powder metallurgy, only the limitation is that the size. You cannot make very huge sizes of aluminum nanocomposites using powder metallurgy route. So your answer to this is whether we can make these aluminum nanocomposites using a liquid metallurgy route or a casting route. So because it's not that easy, okay, the challenges which lie for this making this aluminum nanocomposites is the dispersion of these nanoparticles. Generally, nanoparticles tend to agglomerate, okay, and there are other issues which are associated with this dispersion of your nanoparticles. So if you can produce this cast aluminum nanocomposites on a commercial scale, so nothing like it, okay. And lots of work is being focused on aluminum alloys for elevated temperature applications, which I discussed in quite detail in my last FDP talk. So those who have heard, you must have understood. So this is something which is quite exciting. So to find newer and newer aluminum alloys for high temperature applications. And since the other focus of research in almost all the countries, we are talking about a circular economy, right? You must have heard about this particular word. That means using this all these alloys round and round. That means basically recycling all these alloys. But again, it has its own challenges and issues. So this is something which is needs to be addressed. And lastly, as I mentioned, this additive manufacturing of your aluminum alloys is picking up, but again, this also has its own merits and demerits. But these are the certain areas where if anybody is interested, should think about to work in these particular areas, because these are this is something which is going to stay here for quite some time. So this is some of the research areas which my group does at IIT Bhubaneswar. So we deal with your semi-solid processing, then plastic deformation. We also study grain refinement of different aluminum alloys. Of course, develop new alloys as well, though I have not mentioned here. We work on in situ composites. We work on some other process like your slope casting, and we have some collaborations which help us understanding how this agglomeration of these particles can be studied using your, we call this as a micro CT, micro computed tomography techniques. Then we work on different aspects of your aluminum silicon based alloys and develop new grain refiners as well for the industry, because this is something which is quite exciting, because ultimately you need to grain refine all your aluminum alloys. So some of I'd like to thank some of my collaborators from and I have borrowed some of my slides even from our collaborative work with we have with Brunel University, some with Warwick, and some with your Shanghai Jiaotong University. And also I'd like to thank my collaborators in India from IGCAR, CSI at Trivandrum, ISRO, NALCO, as well as your CSIR IMMT, which is our nearby lab. These are some of the people which I would like to acknowledge: my thesis supervisors, my postdoc advisors, and of course, all the work have been done by the students. So it's nothing without the students. So the research scholars, the master students, and of course the undergraduate students as well. So I'd like to invite any queries, and also please feel free to drop a mail if you have any queries related to this particular talk. I would be happy to answer those. So I would like to thank NMFDO and especially Dr. Debas Mishra for coordinating this particular talk. So thank you all, and any queries, please feel free to ask.
Anybody has any queries? You can directly unmute yourself and ask, sir. or you can type in the chat box.
Yeah, if you have doubts, you can even drop a, you can think and just drop a mail. Okay, sometimes I think we have covered a lot of things. It doesn't come to your mind. So if anything that related to aluminum alloys, just drop a mail. I'll get back to you. Okay.
Good morning, sir.
Yeah.
Sir, I
Yeah.
have a little query about. Actually, it was a nice presentation. What I've gone through this. Sir, a little doubt is there with if there is a casting process that is solid state, liquid state, all those things are casting processes are there. So many casting processes are there. Sir, does it
Mhm.
affect the material properties of the composite?
Yes, definitely. Definitely it will affect because as I told, any casting process, just change the mold, your cooling rate changes, right? Suppose I
Yes,
do
sir.
the same metal I pour in a say mild steel versus I pour it in a say copper mold. Okay, and you know
Yes, sir.
the thermal conductivity of mild steel and copper is entirely different, right? So
Yes, sir.
that what that is going to affect in the heat transfer. That's what mechanical engineers will tell, but what a metallurgist will tell is that your cooling rate of the casting is going to change, right? And
Yes,
cooling
sir.
rate is going to influence the size of your phases, whatever size, whatever phases you have in your material, and that is good enough to change the properties of your material. Okay, so of course all casting processes, the same material made using n different casting techniques will have n different microstructures.
Okay, sir. So for the these casting processes, microstructural analysis is necessary.
Of course, of course. Okay, so since I'm sure are you a mechanical engineer?
No, sir, I am a civil engineer, sir.
Civil
I
engineer,
belong to
yes.
civil engineering department.
Yes,
Actually, sir,
it
I
will
am doing
change.
my PhD in composites, laminated composites. That's why I'm
Okay,
asking this.
yes, yes. For metals it follows, it will depend. Okay. Eh, because it's a it's a temperature dependent process, so it will influence.
So, sir, it may be vary in hydrothermal conditions. Uh, it may be a considerable amount of changes can be observed.
Yes, so I think yeah, for a civil structure also it could apply. I'm not very sure, but I cannot comment on that. But of course for your metal matrix composite it varies.
Okay, sir. Okay, sir. It's okay. Thank you, sir. Thank you.
Yeah, welcome.
Anybody else has any more doubts? Please feel free to ask, sir. I think there are no more
Okay,
doubts. So we will end it up here, the session. Thank you for the excellent session, sir. And thank you for the excellent information on um, aluminum and aluminum alloys and metal matrix composites. And we have learned a lot from you. Personally, I have also learned a lot during the sessions. I have attended 3 4 sessions of yours, and uh, I had a lot of doubt because I'm working on polymer matrix composites. So
okay,
I was not well versed with the metal matrix composite area. So some of my doubts were cleared. So thank you so much, sir.
okay.
Thank you for giving your valuable time to us, to this FDP. Hope to
Thank you.
meet you soon, sir, again.
Sure, sure. Thank you.
Thank
Thank you
you.
very much.
Have
Thank
a
you
good
very much. Yeah, yeah. Bye. You too.